Hello, and welcome to this Vision Systems Design Fall Tech Summit Quick Chat with Euresys. My name is Chris Mc Loone. I'm the editor-in-chief of Vision Systems Design, and today's presenter is Michael Cyros. Michael is Vice President, Sales and Support Americas at Euresys, and his full bio can be found by clicking on his name next to the video. Thanks for joining me today, Michael. And I guess just to get us started, could you describe what is sports imaging and why are we hearing so much about it lately?
Hi, Chris. Well, thanks and good to be with you again. Sports imaging has been an interesting topic. It's been an ongoing topic, in fact, for the past 8 to 10 years in our industry. And you might hear it referred to as stadium imaging or sports analytics. We refer to it generically and broadly as sports imaging. However, COVID has really accelerated the demand and uptake of this technology. So you see it being deployed in all types of applications. For example, remote audience participation. If you remember during early COVID days, when the NBA set up a limited set of teams in their bubble in Orlando, Florida, they made the games feel live by having spectators virtually present. Basically, there was a monitor in each seat and each user connected by video conference. That caused several challenges, in fact, because it was done with standard video conferencing technology. And as soon as that industry discovered the capabilities of machine vision cameras, it quickly migrated over to that. So you see examples in remote audience participation. Another great example is dynamic interactive viewing as a premium paid service. So you can imagine a football stadium surrounded by high resolution cameras. Very low latency cameras and all precisely synchronized and triggered. The viewer could dynamically move their own view around the play action. And every person at home could customize their view by the sense of all of this content. Another big area is in augmented reality and virtual reality. So 3D kinetics or 3D motion analysis or play scene analysis, for example, batter swing analysis in the sport of baseball, golf swing analysis, and so forth. 3D player tracking. You've seen more and more use now in football, hockey, and other types of sports where the scene that has just played out live on air is replayed in virtual three-dimensional space with real video. So that means that machine vision cameras are imaging that scene, multiple cameras, and on the fly processing that for 3D viewing so that they can go back after a commercial break and play the scene in real time. You've seen cases of projecting score lines or fault lines or offside lines and so on and so forth onto the field dynamically. Those aren't there for the live spectators, but that play experience is able to be augmented with digital imaging technology that comes from our machine vision industry. Dynamic advertising content, for example, where depending on where the scene is being played, or aired, I should say, you can change out the advertising content for local markets. Capture real video of real players in 3D for computer gaming scene generation. If you've played any of the latest sports games on the latest gaming platforms, the play action is so real. I mean, it really looks like the live players that you're interacting with on the screen. And all of that is captured using machine vision technology to construct those games. And finally, for virtual reality, interactive training videos, where your motion can be analyzed and a remote coach or player can help you improve your game as well. So there's a lot of areas in sports imaging where machine vision technology comes to play.
Okay, those were a lot of very interesting applications. Could you get into some of the specific machine vision-like functions used in these applications?
Right. So yeah, this is an interesting question because there are many techniques that we know in traditional machine vision. For example, precisely triggering a camera. For example, when a part is coming down a conveyor belt, and enters into the field of view, a part in place or some type of sensor is triggering the camera to take a very an immediate image for analysis. The same thing needs to happen in sports imaging. So the ability to precisely trigger cameras is a really important feature. Not only do you need to trigger cameras one by one, you need to synchronize that triggering across multiple cameras, multiple and even multiple PCs. For example, if you have a distributed edge type scene processing system, you need to make sure that all the cameras are precisely triggered so that the image scene is captured at the right time in the three-dimensional space. 3D calibration and processing for 3D scene reconstruction. So the same ability to, or the techniques used to make three-dimensional measurements of a part that's being manufactured are used to construct the 3D positions of the players that are moving about the field. So that's an essential feature for this 3D scene reconstruction, where after a score has happened in a particular sport, the replay action can show the play action in three-dimensional video and allow the viewer to virtually move around that play scene. So all of that requires 3D calibration. Of course, gen-locking cameras across multiple PCs is critical. One of the reasons for that is what's known as anti-flicker processing. So for example, different stadiums, whether they're indoor or outdoors, are using different types of lighting. In the early days of machine vision, typical lighting was based on AC power, so the lights were cycling at a 60 hertz rate in the Americas, or 50 hertz rate in other parts of the world. And in all those cases, it was important to synchronize the camera to the lighting so that the start of exposure would happen when the light is at its brightest illumination point. Now, fast forward to modern day today, stadium lighting, for example, LEDs and so forth, the intensity is still modulated by those LEDs that are flashing at a very high frequency, 200, 300 hertz, for example. So in that case, having a Genlock signal that's synchronized to the lighting is critical to synchronize all of the cameras. And you could be talking 50, 60, or even 100 cameras spread around a stadium for all of this imaging. And speaking of spreading multiple cameras around, spatial calibration of the cameras for ease of post-processing and stitching across multiple images is also important for scene generation. You can imagine, panning across a field where down the field there's 20 or 30 cameras focusing on the play action. The view needs to transition seamlessly and smoothly from camera to camera as the play is happening. And then finally, as what we know in machine vision, is the importance of guaranteed sustained bandwidth of images coming to the PC for processing with minimum latency, are all requirements that are essential in sports imaging, and they're the same techniques we use in traditional machine vision.
When we talk about the applications that you just mentioned, part of that has to be the pipeline to get all of that information back to wherever it is going to be processed and possibly decisions are going to be made. What are the most widely used currently camera interfaces in sports imaging?
Thanks, Chris. That's actually a good question about those interfaces. Traditionally, in sports imaging, high-speed broadcast cameras, for example, recording in 4K resolution at 30 or 60 frames per second for broadcast is done over HD SDI. HD SDI is run around the stadium either in fiber optic or coax cable. Some stadiums may have Ethernet wiring. So the two dominant machine vision interfaces that are used are indeed GigE-Vision and CoaXPress. Both, in fact, are good, but each has its own set of benefits. So a typical stadium setup may determine which of the interfaces are better. We tend to focus at Euresys primarily on the CoaXPress interface, but we also are involved in GigE-Vision through our IP cores. In fact, we're in the process now of developing latest generation 25 GigE-Vision IP cores for the industry, which is going to require an adoption of the GigE-Vision standard up into these higher speeds. Those speeds already exist, in fact, on the CoaXPress side, where you can have multiple lanes of 12G video. So differences between those with GigE-Vision, of course, you're routing data through switches and hubs and networks, which is really convenient. But you, in some cases, lose the ability to easily synchronize multiple cameras in that case. And this is an area where, for stadium imaging, CoaXPress really shines. CoaXPress is, in fact, a point-to-point interface. It runs on traditional standard coax cable that's probably already run in the stadium, or even fiber optic with the latest technology of CoaXPress over fiber. So these networks of cabling are already existing in many sports imaging. You know, there may be coax cable and fiber optics, as mentioned, which CoaXPress can be adopted to run over, whereas for gigabit Ethernet, it can be adopted for fiber, but again, you're dealing with the need to go through switches and hubs rather than dedicated point-to-point interfaces. So we do see both, but however, we see that lately in these applications, the push has been for high-speed CoaXPress because of the proliferation of so many cameras around the stadium.
Well, thanks, Mike. And that gives us a pretty good snapshot of where we are right now. But what's in store for the future?
Well, I think what you're seeing already in the home broadcast market is the growth in resolutions of displays. So, for example, we're just now in mainstream 4K broadcast resolution. 8K is there, and imagine a television set that's going to display 8K video at 120 frames per second. That's a huge amount of data. So the ability to speed up data across these camera interface networks is really important. So we see already emerging 25G interfaces. Multiple 25Gs can be streamed together to generate 100G, and the same thing is happening now at 200G and 400G. So that's, when I say G, that's gigabits per second of data. So it's a huge amount of data to process, and along with that, PCs are getting faster. And commonly available GPUs that are developed for the gaming industry and image scene generation are essential also for processing all of this data in stadium imaging. So advances in GPUs are really growing also, which allows all of this processing to happen with this much data.
Okay, perfect. Well, thank you again for your time today, Michael. Just a reminder that this session will be available here within the Vision Systems Design Fall Tech Summits platform for the next 30 days. To find more information about Euresys or any of our sponsors, please be sure to visit the Resource Center within the event platform. On behalf of the Vision Systems Design Fall Tech Summit team and our sponsor, Euresys, I thank you again for joining us today.
Thank you, Chris.